Hello everyone. It's lovely to be here, and thank you for inviting us to this lovely event. I don't speak any Korean, so you'll have to put up with my terrible English. My name is Giancarlo Pierce, and I'm the Business Development Manager and Localization Supervisor at Area 35, and this is my esteemed colleague, Mr. Daniel Dressler, who is the lead programmer at Area 35 for Tiny Metal. A quick word of note about this presentation is that all materials have been cleared for public release. This is a little bit about us. I'm sorry, it's in English. And please allow me to make a quick introduction about our game. Tiny Metal is a turn-based military strategy game developed for the Nintendo Switch, the PlayStation 4, Windows, and the Mac OS using the Unreal Engine. Tiny Metal currently features a single-player campaign mode, skirmish mode, and a soon-to-be-released multiplayer mode. You'll be glad to know that the Korean version of the game will also be released soon. Without further ado, allow me to introduce the topics that we will talk about in this presentation. Real-time rendering, the future of CG cinematics, getting the most out of the Unreal Engine, the architecture behind Tiny Metal, the benefits of using LiveData for efficient games development, how we optimize the game for the Nintendo Switch, traditional three-point lighting versus newer, more modern techniques, using Unreal Motion Graphics, or UMG, for consistent UI styling. Finally, our use of the navigable menu, or navigable menu, to create a cross-platform UI framework. Now, to move on to our first real topic, real-time rendering, the future of cinematics. So, let me set the scene for you. You are a small indie dev studio that would like to make a movie for your game. You know it would be good marketing and PR. And your basic needs are the following. You need something with high production values that is able to convey your game world and message in seconds. Finally, you want something that is aesthetically pleasing, that is able to cut through marketing noise, and is hopefully visually very cool. Up until now, however, making movies was a complicated and hard process that added extra financial strain upon already extended budgets. And most of all, they simply took a long time to make. Now, you still want to make that movie for your game. What are your options, and what can you do? The answer lies with real-time rendering. Many of you here, of course, would know what real-time rendering is. Historically speaking, real-time rendered video content made using, for instance, a game engine was of subpar quality when compared to its offline pre-rendered counterparts. However, with the recent advances in technology, the gap between offline pre-rendered content and real-time rendered content is becoming very blurred. Let us take, for instance, our own opening cinematic for our game Tiny Metal, which was made using in-game assets. I hope this works. that wasn't too bad. This whole thing only took us about maybe just 1 week to make. Being an indie company, we lacked the budget of some of the other larger studios. We had to explore all of our available options and come up with a smart economic solution to our problems. With real-time rendering, we found that you can now create quality movies with assets used in your own games. Your models, animations, sound, all of it can be used. Here are some more advantages of real-time rendering. Real-time rendering allows for very fast iterations. You can see the changes you make in real time, which makes direction and verification of changes made very easy to do. Feedback can be easily incorporated, and the faster iteration cycle means that there is more time for experimentation. Real-time rendering benefits from a very fast R&D cycle. Since iterations are faster, we can try new things. This is in comparison to slower traditional methods, where experimentation represents a larger investment in both manpower and time. Real-time rendered content is also very easy to edit. Sound and music can be checked and edited in real time, and if you have all the assets at hand, it is a job that can be done by yourself. Editing can be done using Premiere or Pro Tools, which means that hiring sound staff is no longer a requirement. All of these changes can be, of course, be made using the Unreal Engine. The trailer that you just saw was made completely by just one person. Finally, there is no need for compositing. Originally, composite works was a pipeline designed to save time with CGI works. For instance, in the composite pipeline, you can adjust the intensity and color lighting separately in post-production with a foreground, background, mask, and so forth. However, since everything is now rendered in real time, this part is no longer required and can be simply ignored. In conclusion, with the advances in modern technology, the gap between offline pre-rendered techniques has been all but closed. Real-time rendering not only has a lower cost and faster production times, it also has a quality that rivals that of offline techniques. Allow me to finish my part of this presentation with a short movie by Mr. Erasmus Brosdow that was made exclusively using real-time rendering techniques on the Unreal Engine with minimal resources and in the record time of just about 1 month.
Old growth. Makes you feel small, doesn't it? Gotta keep it moving, guys. Objectives right ahead.
Alpha 1 to HQ. We've got a visual on the anomaly.
You seen this? Looks like it just burst its way up through the ground.
Scanners are saying it goes deep. Real deep. But no life signs. Hold on. Got something here.
Contact! Moving quick!
There! In the tree line!
Can't lock it down! Shit! Where is it? Get those shell units into combat formation!
Shield out! Taking fire!
Anyone got a look? Call your targets! Yeah. I've got weapons. Fire, I will!
HQ, this is Alpha 1. Requesting immediate URS.
Fall back! Into the woods! Come on, go!
I'll pass you now on to my colleague, Mr. Daniel Dressler.
Right. Hello, everyone. I'm Daniel Dressler. I was a program. Oh, thank you. Oh, wow. Thank you. Oh. I mean, I haven't spoken anything yet, but okay. I was a programmer on Tiny Metal, and one of the big constraints we had with Tiny Metal was we had only one programmer. But we wanted to ship on 3 platforms. So we shipped on the PlayStation, and we shipped on the Nintendo Switch, and we shipped on Windows. And the only way we could do this was thanks to Unreal Engine. So I'm very thankful to Unreal Engine for both allowing us to make our own game, making it possible for to make me my dream game, and then now I'm thankful to Epic Games for flying us out here, and I hope this presentation will be able to help you in your work. So one of the things I think a lot of game developers should consider is that Unreal already provides a lot of the tools you need to make your game. You don't need to make a lot of custom things if Unreal already makes it. What Unreal made and is giving you is already enough to ship your game. So you should plan to use Unreal for most of the things. Then you should plan what is the most important part of your game, and then you should make that special. So for Tiny Metal, we use almost everything just normal Unreal. This is actually the camera in the game, right? That's the cursor for the player, that's a camera arm, and then the camera's right on that edge. And we have some complicated behavior on our camera. If you have an event on the other side of the map, the cursor needs to zoom all the way over there, and it needs to speed up. And historically, if you were going to program an RTS, you'd program some very complicated behavior. You'd calculate things like the bounding box of the screen, and then you'd calculate if something is in that bounding box. But with Unreal, you don't need to do that. We use that camera arm, and then what I do is very simple. If something is in the bounding box, we set the latency on the lag to, I believe, 0. So it actually just disables the lag, and so the camera doesn't move, even though the cursor's moved. And then if the cursor comes out of the frame, I make sure that the lag goes back up. And so then the camera just moves in closer. When I tried to program behavior like this in other game engines, it was very difficult. I had to program vectors and I had to deal with screen space and world space and vectors transforming between those world spaces. But actually, what I should have been doing is doing what Unreal has provided and just using that. And so that is how we program our camera. It's actually really simple. And now if I want to make another camera like that, I know how, and it'll take me 5 minutes. So the biggest thing I think developers using Unreal should learn is learn how to make every part of a game using just the Unreal parts. And then figure out what's special about your game. If you know what's special about your game, then you should put a lot of your time into that. So for Tiny Metal, this thing that was special about our game was the gameplay. People did not care so much about the visuals, but they really cared about the gameplay. And so for us, it was very important that we had our own gameplay engine, and that's BattleCore. BattleCore provided a lot of other benefits, but the biggest benefit it provided nowadays is our AI runs entirely on a simplified version of the game state, which means that our AI, when it plans to make a move, it pretends that it moves across everywhere on the map. It pretends it moves every unit and attacks every other unit, and then it decides the move it likes the most. It's a very simple AI, but it's possible because it crunches so much data. And it's only possible that it crunches so much data because it's not touching anything on Unreal. If you try and program an AI using just the Unreal behavior trees, you will not be able to have probably more than 5 to 50 units. BattleCore can support up to 300 units and will not slow down the gameplay. But that's just because, for us, that was important. For your game, it's probably not important to have 300 units. And so you need to find what's important for your game and figure out how to make that really, really good. And then leave everything else Unreal. So let me talk about what I did do for Tiny Metal. Right? So for Unreal, for Tiny Metal, we used Unreal for all of the hard stuff. All the stuff it's no fun to program. So Unreal handles all our rendering, our visuals, our interactions, all the user interface, all of the cross-platform support, all of the, what's another really boring thing? File systems. File systems are really boring. Unreal does all that for me. I don't have to worry about file systems. I actually did have code in the code base that did file systems, and then it turns out it breaks on some platforms because Unreal does some really cool stuff with compressed data. And so I just had to start using the Unreal file system stuff, and my life got easier. My life got easier the more I used Unreal. Now, Battlecore is a system that I wrote. I talked about it. It's our gameplay system, and it is entirely separate from Unreal. There is no Unreal code. There is no T-array. There is no T-map in Battlecore. Battlecore is in 100% C++ 14. And then LiveData is also something I'm really proud of because it turned out to be really helpful for us. It handles all the content, all the rules. So anything that you might have a level designer dealing with, or someone who's adding rules or balancing the game, LiveData takes care of that. LiveData also is mostly programmed in Unreal. And so one of the things, though, when I was trying to really, I think it was probably the third time I really started to really program the game, is I could not figure out how I should use all of these Unreal nouns. What should be a pawn? What should be an actor? Should I use the player state? Should I use the player controller? How should I use a player controller? So this is how we use the Unreal gameplay frameworks, but this is probably not how you should use them. This is how I thought to use them when I didn't know how to use them. But hopefully you can look at this and you can figure out a better way to use it for your game. So for example, if I were to redo everything, I probably would use player state. In Tiny Metal, we used almost no player state. We use the player controller, but we use almost none of the player controller. In fact, things that should be in the player controller are in the pawn. And in fact, you can't really switch pawns. I didn't program it thinking you could do that. But if I were to redo it, I'd make sure that I could switch pawns, and I'd add more control and more state into the player controller. But you can ship an entire game using the Unreal gameplay framework poorly, like I did, and it'll still work. Unreal has all these tools, but you won't get into trouble if you don't use them. But you should use them because they help you. Okay, so Battlecore is 100% C++ 14 integrated with Unreal Engine. And there's a thin piece of Battlecore that talks with the Unreal Engine, right? And so all of the gameplay logic, all the things saying like this unit exists here, this unit has this much health, that's all in Battlecore. And then what the Unreal code does is it asks Battlecore, can you give me this unit? How much health does this unit have? And one of the things I've learned over my years being a programmer in video games, it's very important to have only one source of truth. One place where all your data is, and not two places with your data. Because once you have two places that have the same data, then you have cache invalidation. And it just gets a lot harder. So we made sure that there was only one place where everything was implemented. But there's more than that, because actually, Battlecore is not one instance of Battlecore in Tiny Metal. Tiny Metal is structured as a always networked game. Even if you're playing just one person on a switch, the AI itself is networked as if it's a multiplayer instance. Not using the Unreal networking, but using Battlecore's own internal networking. And this allowed me to do things like hack in some state reading. For example, one of the things when I was first trying to program a turn-based strategy game is if you're doing an animation and this animation tries to attack another unit, but someone else wanted to read that unit, read it exists, you might run into race conditions where that unit's already been killed. It makes it very hard to deal with animations. It makes it very hard to deal with AI. So what Battlecore does is every AI has its own entire copy of the state of the game. And then it's synchronized using events. So Battlecore replicates everything using events. There's a fancy Gang of 4 pattern name for this, which I don't remember. I didn't base this off of the Gang of 4 patterns, but I think it's the command pattern. And it works out pretty nicely. This is all of the events in the game. Now, these are not the actual events. These are the APIs where the events get submitted to the simulation core, which is a part of Battlecore. And so we can see stuff like, let's see here, burst. That actually doesn't exist in the game. It's an event that's programmed but never gets used in the game. But I left it in there because it actually doesn't cause any issues to leave that gameplay functionality in there. No units have the permission to use that burst, but the code just works. All right, so some benefits of doing it this way for our game. It's probably not going to be the truth for you, and there very well are a many number of turn-based strategy games that do not do it this way. They just use Unreal, or they just use the gameplay framework as provided. Because effectively, Battlecore is another gameplay framework. And there was a lot of overhead and work I had to do because I was also essentially maintaining a secondary game framework. But it meant that I had one code path for all things in the game. If a player created a unit, that was the same code path as if a unit was getting loaded from a save file. And when I've tried to program games like Tiny Metal in the past, this was a big problem for me. I had to try and save out, oh, this unit was created, therefore I should play an event, but this unit was loaded from a save file, so I have to have some code path that says, well, this wasn't created recently, so don't play the event. Otherwise, you might load the map and have a bunch of these sparkle effects spawning off all the place, which probably isn't actually a big issue if you're using the Unreal game framework. Well, actually, that kind of still is. It depends on how you implement your saving. There are other games that do this kind of lockstep instantaneous eventing. For example, Age of Empires is famous for having a lockstep simulation while still submitting events. A lot of Japanese fighting games use lockstep simulation, but then they submit key inputs. Tiny Metal, because it's submitting events, these events encode all the side effects. And so we can have full randomness on the client side. So if you're connected with another person, there's no need for actual hard synchronization. So one player might be seeing an animation that lasts for 5 seconds, while the other player might be seeing an animation that lasts for 3.5 seconds, and it might be entirely random, but doesn't cause any problems because the side effects have been synchronized. Which also means that we don't have to wait for any network latency. So a player will receive an event, start playing the animations, but they don't realize that that event actually got sent a couple seconds ago. They've been on their machine exploring the map, and they have not seen any form of latency, no lag. And that's a pretty big deal for a turn-based strategy game. Well, it's nice to have, I guess, actually. It's probably not a big deal for turn-based strategy games. Real-time strategy games have a lot bigger issue with latency, but I liked it all the same. So LiveData is how we stored all the game data, all of the content, let's see, all the game rules as well, and the localization. The localization was a big deal. It turned out to be the biggest file. And one of the things we ran into is when you start programming your game to be entirely content-driven, that is to say data-driven, to say things like there's a line in a spreadsheet that tells you what weapon a unit holds, you can do fun things like this. These are all screenshots I took during development when something funny happened. So up there is when I accidentally stuck a tank cannon on a infantry unit, and I thought it was really hilarious because it's gigantic. And we ran into this actual issue where the artists never used a consistent scale on their models. So that tank cannon's not supposed to be that big, but because we were relying on Unreal's child instancing, not child instancing, the scale, okay, so in Unreal, if you have a actor, and then you stick another part on that actor, that part will inherit the transform, including the scale. And it turns out our artists relied on that heavily because they got all of the scales right between a single unit, but every unit had a different scaling. So tanks were super massive if you didn't scale them down. But in my experience, that's actually very common. Artists create lots of messy data. And it's very good to make sure that there's a point in time when you can, as a programmer, scale or change things. And so that's why we don't have any implicit linking on the art side. Implicit linking is something like, if this file name is X, then it is the part for this Y. And then there must be also an icon also called X. That's very popular for programmers because essentially all we're ever doing is implicit linking, and it means we don't have to do as much typing. But the problem is artists like doing things like having very inconsistent file names or inconsistent scales. We even ran into a point where our particle systems, the artists were using inconsistent scales, so we had to ask Epic Games to add a feature to the particle effects system to let us scale particle effects. And it's now in Unreal. And that was useful because artists are really messy. Okay, that's kind of a side tangent about data-driven code. It's really powerful. Try it in your game. But what it allowed us to do is live reload. Everything was in a spreadsheet on Google. And then those buttons you see on the top, a planner, which is a Japanese job position. A planner is someone who does level design. Essentially, they do everything which is not art or programming. They can click the button, and then the LiveData will talk to a proxy server. The proxy server will talk to Google Spreadsheets, will grab the data, format the data, and bring it back to the game. Early on, it was really quick. It took seconds. But as time went on, the more data we had to pull from Google servers got bigger, and now it does take about a minute. But what you can see, though, is we still have relatively small file sizes. The words is our localization database. It's 3 megabytes, which sounds pretty large, except we have about a novel worth of text, and we ship in 10 languages. Fax is the game logic, and it's pretty small. So it loads really quick. Okay, the idea behind LiveData was very simple. My experience in the Japanese games industry is game planners really love Excel. And if you don't give them Excel, they will, for example, if you try to give them a JSON file, and you said, please edit this JSON file, and then you can make your map. Programmers love doing that kind of thing because programmers think this lets the game designer or game planner make all the content. But then the Japanese planner will come back and say, thank you for giving me that. Here's the Excel file. Can you please do that for me? And so you cannot get away from Excel in Japan. And so I figured, I'm not going to fight that. Let's give them Excel. And so we gave them Excel. It turns out they actually don't care whether it's Microsoft Excel or Google Spreadsheets. It's all Excel as far as they're concerned. So Google Spreadsheet works really well. And so, as I mentioned earlier, I programmed a proxy server, and this proxy server runs on one of our servers. And this proxy server has the implementation of the Google Spreadsheets API. It then asks the Google server, can you please give me the data from this spreadsheet? Then it formats it into a flat buffer object. It's this flat buffer object that gets sent to the game. And this is very important because the Google API is really hard to deal with. And there are no good implementations of it in C++ or anything you'd want to ship in your game. And there's a secondary big issue, is that consoles do not allow you to do this kind of live reloading. And so in the console version of Tiny Metal, that code that contacts the server is compiled out. And what the game does is it only loads the game logic and the localization from the flat buffer data cache on the disk. And this took almost actually no work. There's just a small piece of line saying, don't bother contacting the server, and it by itself falls back to reading from the disk, and since the file is always there on the disk, it works. It also means that if we wanted to patch just the game data, we could send out a patch with just that file on the disk. So for us, and this might not be such a big thing in Korea, but for Japan, the Nintendo Switch is a really big deal. Most game companies are focused on developing console games. They're the most fun to develop, and it's what the industry has a lot of experience. And for us as well, that was a big focus for us. The Nintendo Switch actually is our biggest platform. For every 3 people who played Tiny Metal, 2 of them played that on the Switch. And so we knew the Switch port was going to be very popular, and so optimization was a big priority for us. I spent more time on optimizing for the Switch than I did for most other tasks in the game. And I needed to spend that time, because when we first ran Tiny Metal on the Nintendo Switch, it ran at 7 frames per second. It was really bad. And as you can see here, though, this is a screenshot of the PC development. The truth is, because of NDAs, I can't talk too much about anything Switch specific. So what I'm going to talk to you about is how I optimize things for the PC, because that's actually what I did. Because we did not do anything very complicated. As I talked about earlier in the presentation, if you just use what Unreal provides, that's enough to ship. So our rendering code is not very special. In fact, it might be very boring. There's no customization of the render pipeline. It's just standard materials. And our lighting wasn't anything special. It was just a bunch of directional lights with some special features used. But what I found out was that actually those special features were not used very well. There were a lot of lights which were not doing anything, but maybe even had shadows enabled. There were lights that were so faint, you could not really see. You could when you turned them off. You could tell that they weren't there, but they were not adding to the game. But they were making the game much slower. So much of my optimization was focused on finding out where our GPU time is being spent, on what lights it was being spent, on what special features it was being spent. And so I did things like disabling motion blur. Tiny Metal does not use any motion blur, even though it's enabled by default on Unreal. And I tried to optimize the shadows, which is a big deal because we are a game in a top-down perspective. A lot of the technology in Unreal is designed for games that have a horizon you're looking at, very far view distances. But because in Tiny Metal, everything is about the same distance from the camera, we don't get to use any level of detail. Everything has the same level of detail. And so I need to make it fast. So I used tools like RenderDoc on the PC to understand what was getting rendered. And we had things like the fog models were getting rendered across the entire map. Now, fog in our case is just the name for the tiles which are not gameplay tiles. And so we have a lot of not gameplay tiles, but they were getting rendered. And so I used tools like this, which Unreal provides, to understand that I wasn't using Unreal correctly. And so optimization for Tiny Metal wasn't anything amazing. It was mostly just me understanding where we made mistakes. Now, because from the very beginning I had used static instance meshes for all the terrain, we did not have a draw call issue. our draw calls were always under our draw call target, which would run, I can't talk about the target because of the NDA thing, but I would say that it's a number small enough that you could use it on the phone. And so by our release date in November 2014, no, it's not 14, 2017, we had 30 frames per second on most maps. But there are some compromises I made. Things like in our battle scenes where we zoom in and we show a higher detail version of the map, we also use more lighting effects. And because we use more lighting effects to show more detail, I couldn't run at full resolution. Actually, Tiny Metal is a bit special. Tiny Metal is, to my knowledge, the only game using Unreal on the Switch that does not do any upscaling, except for the battle scene. Outside the battle scene, Tiny Metal runs at 720p. It runs at full resolution with no upscaling. But I also couldn't use any bloom because it turns out that was just slightly too expensive. And it was really painful because it's not that expensive, but it was just a little bit too much. But there's still room to improve. And so right now in the current development version of Tiny Metal, I made things even faster. And the biggest way I made things faster was by using instead of the deferred rendering pipeline, we now use the desktop forward rendering pipeline. And we are 30 frames per second on all maps. And the battle scene is full resolution, no downscaling. And everything looks better. And the lighting is just one light with global illumination. It's actually gotten very simple. And I kind of want to talk about that because we went through a problem, which is our problem is when we started development, an artist who was very experienced with Japanese games set up all the lights. But they set up the lights using the traditional three-point lighting system. And as I went on, much of what I was doing was removing the traditional three-point lighting system and moving us towards a more modern lighting system. But I didn't understand that. I thought every time I was changing it, I was just making a small change. I wished someone had told me that I should have deleted everything from the start and went with a simpler system from the very beginning. And so the three-point lighting system was designed for the real world. It's a concept that photographers and cinematographers have when they already get to use all the real things in the real world and they want to make something that's fake. They use three-point lighting system to pretend that someplace indoors is outdoors. And it works very well for them. But for video games, we have already simulation everything. And we aren't trying to make something that is real look fake. We're trying to make something that's fake look real. And so the better way to do that is to use a simple lighting and then all the lighting features of Unreal. Right? If you use a three-point lighting system, nothing is physically accurate because there is light coming from directions where no light should be coming from. You can't do things like have time of day because then you'd have the backlight facing on someone's front light. Instead, you have to have artists set up multiple lighting profiles for indoor and outdoor and evening and night. And because you're rendering so many light perspectives, it gets pretty expensive. And so what Unreal provides is more modern lighting techniques for video games. Things like skyboxes are very old, but on Unreal, that skybox can provide lighting information. You can use baked static lighting, which allows you to then also get this baked bounce lighting. Or if you use ambient fog, it's way better than the old GPU-based just fog out panel. It gives you the same effect that you would have if you were standing on a mountain and looking in the far distance. And it's also pretty cheap to render. And so this is a screenshot of a game Naj by Osmat. I love it because it's so beautiful and yet so simple. Most of the art assets are the same, and the lighting model is not anything very special. This is a game he made in his free time. And yet, if you were to show the screenshot 5 years ago, it would look like magic. And that's really, I think, the true power of Unreal on the rendering side, is something simple can look really good. Now, this is, I think, a topic that probably even you in here, Korea, are having issues with. UI in Unreal is very hard to work with. I love UMG. I think it's a great layout engine. I think it's really powerful, way more powerful than Unity's layout engine or the web layout engine. It lets me lay out things really well. It scales very well. And there are only a couple edge cases that I have to worry about. Now, for Tiny Metal, we had no UI designer. And so I did most of the UI design. But I'm really bad at UI design. And so we had some goals, right? We wanted everything to look the same. It needed to scale down to the Switch, which is actually a goal we've kind of failed at when we released. A lot of players said your UI is too small. And so if you're going to release on the Switch, I encourage you, make your UI bigger than you think it should be, because players want it bigger. Also, it needs to be translatable, because, of course, everything nowadays needs to be translatable. And so for that, we use LiveData. But the biggest thing is it needs to be consistent, because if your UI is not going to be very good, because you have if you have your programmer designing your UI, then it should at least be consistent. But it's really easy to make consistent UI in UMG, because UMG lets everything get nested. If you create a user widget in UMG, you can include it in another user widget as if it itself was a user widget provided by Unreal. You can even extend user widgets from C++. So that's how we implemented our translatable UI in Tiny Metal. Is I took the text widget that Unreal Engine provides, I made a child class of that, and then I programmed my logic for looking up the text, and then it just instantly magically appears in the editor for UMG. I was very surprised, because that's clearly the power of those reflection-based systems Unreal has added to C++. I did not imagine that just simply subclassing an object or subclassing a class would allow it to appear in the UMG editor. And from this system, what we ended up doing is creating basic components. So what we're looking at now is the pattern. And this pattern gets used all over the place in Tiny Metal's UI. It used to be simpler, but what I learned is you can use shaders in UMG. And so this is actually a pixel space shader. And then, so if you take a UI in UMG and you scale it down, any of the images in it will get scaled down themselves. And it will not do a very beautiful looking scale. It will be a very simple scale. But if you program your logic in the shader and you implement it in pixel space, then even when the UI scales down, the shader stays at the same resolution. And for our pattern, that was really good. It means that on the Switch, this still looks crisp, even though the UI is getting scaled down. And so from this pattern, we created the common background. This is the motif of all of Tiny Metal, is this simple pattern with a little color on the top. And we got a lot of mileage out of it. So that common pattern and that common background is how we made the buttons. And we have one button in the entire game, which we probably should have more types of buttons. But since I designed the buttons, we only have one button. And then we made this. Actually, this is not really a button, but this is our main menu. And I programmed it to be relatively general. And so one of the nice things about Unreal is everything fits together. So the way that I programmed this is it takes a struct. And the struct has a struct of structs. And so if I want to add an option, I just need to add a string into the fancy menu item options. And when you program your UMG to just take a struct and then build out the actual thing, you can do things like reuse the main menu for a dialogue. So this is actually the main menu code as also used for the "Are you sure you want to delete your save" dialogue. It took me about an hour to add this dialogue. And that made me happy because I thought it was going to take me a lot longer to program this dialogue. But because I could just reuse what I had already programmed in UMG, add it into another slot and reuse the pattern in the background, I could make an entire system. And this allowed us to pass lot check. But one of the biggest things we ran into from the very beginning was UMG does not provide a good way to handle input. So if you are programming a game for mobile, this is probably not a problem. If you're programming a game for PC, this is probably not a problem. Because UMG does a very good job of giving you buttons. And these buttons will listen to a key. Or sorry, they will listen to a mouse. And they will listen to a touch. But they will not listen to a button of a remote control of a controller. And if you're on that controller and you press up, UMG will not tell you or give you a way for that up to go to another button. And that's a really big deal for console. We have to have things like settings menus. We have to have things like configuration of the rules for a session. These are not things that we can just use A and B for. We need to actually allow users to change focus and navigate around the menu as they do in all the other really cool games they play on their console. And what some other games do is they re-implement another copy of their UI. They maybe hire a porting house to reprogram the entire UI. And then they are done with it. They don't worry about it. But we only had one programmer. So I only get to implement the UI once. And I can't do it twice, because if I did it twice, then it would have to be half as complicated as UI. But we actually didn't have any extra UI. So we needed to make sure it worked really well the first time I did it. And so we needed a piece of code that would allow us to make one UI that would work with keyboard, with mouse, with touch if we wanted to implement it, and very much work with controller. And that means it has to have a single code path. It has to have concepts like focus and priority, so that if you go back to an object, it highlights the thing that was highlighted last. And I wish Unreal provided this, but it doesn't. And I think it's something that Unreal should provide. But what instead we've done is, this is the code we used in TinyMetal. It's not very beautiful. It's very ugly code, but we went and open sourced it. So you can use it in your game. It's licensed on the MIT license. It's very bad code. So maybe don't use it, but maybe you do need to use something like it. Because if you're shipping a game on multiple platforms, you should not be rewriting your code. So please consider looking at this code and understanding how you want to do it for your game. It will save you a lot of time And your users will be much more happy if you put all of your time and effort into making one version of UI the best it can be than to try and make different UI for each platform. Now, if you're only on mobile, this is not a problem. You're fine. But if you're trying to ship on console and PC and mobile, then you should try and do this. You should try and find a way to have one UI. And this is, and maybe think about this. So the way I structured navigable menu is it's somewhat modeled off of the web's model for input. And so what that means is when a key, if a user presses an event or the up button, then it starts at the root of the UI and it says, here is a button. And that root can then do something, or it can pass it to its child that has focus. And that child will say, I want to do something, or I'll pass it to the child that has focus. And it goes all the way down to the end node of the input graph. And so what is often at the end of that input graph is a button. And this button says, you pressed A. And then it will say, well, my name, I am the button called cancel. And you pressed A, so I'm going to give the result cancel. And so I'm not sure how well you can see from here, but this is the results occurred of the main menu. So if the user presses A on the main menu, and the button that gets that A, that had the focus, will give back the name, I am menu direct connect, I am menu LAN. And then the menu system that owns the main menu will say, well, I know what to do with menu direct connect. Let me go start off the Wi-Fi direct connect service. And for example, if we want to have a scrollable menu, there is a small event in the framework called child focus event changed, which fires off if the child changes, or the child which has focus changes. And then the parent says, well, I know who you are, and I'm going to use the UMG API for making sure you are the thing in the scroll menu. Navigable menu does not worry about that concept of visuals, or what is in focus, or what can be seen on the scroll menu. It's only concerned about navigation. And then UMG, it handles the visuals, which is what UMG is really good at. And so that gives a separation between the UI behavior and the game logic. And this is really important because it means things like our main game menu can be programmed from a structure, can be configured from the structure, which is how I was able to use it in the dialogue as well. And the thing that owns the main menu has to deal with considerations of how do I do Wi-Fi Connect. There's one code base for all platforms, and I can take one widget and I can stick it in another widget, and it just works because they all just use navigable menu. And I don't have to program it to go, well, from that button, if you press down, you go to this button, because I put those widgets inside a thing that already manages that, which is composition. It's very common in all programming, but if you don't use a system like navigable menu, you will not get that in UMG. And so I think you should maybe use something like navigable menu. I think if you can program something yourself, you should. I think everyone should probably take a look at the navigable menu code and decide for yourself if you want that. Oh, and one of the other benefits is it makes it really, really easy to fire off events. And so because of that, almost everything UI in Tiny Metal has a transition event, or a transition animation. And I'm pretty sure we have more transition animations than any other game using Unreal, because it was really, really easy to add. Now, thank you everyone for listening. I hope you got something useful. Oh, actually, does anyone have any questions? I love answering questions. Please ask lots of questions. Oh, there we go. Question. I love questions.
UMG에 관해서 좀 질문이 있는데요. UMG 같은 경우에 지오더 관리가 좀 정적인 면이 있는데 혹시 개발을 하면서 동적으로 위젯을 생성을 해가지고 붙이거나 떼거나 하면서 지오더 관련해서 관리를 했을 때 특별한 이슈가 있었는지 혹시 있었다면은 어떤 방식으로 해결을 했는지가 좀 듣고 싶거든요.
Sorry, by G-order do you mean rendering order?
예, 렌더링 오더 말하는 거예요.
Okay, we had no problems with rendering order unless you're referring to adding multiple instances of a. How should I say this? For Tiny Metal, we added almost one user widget to the user's screen, and that was the main HUD. And then we used navigable menu to add children HUDs. And these events already passed their input, and so we added only one other thing that needed to be ordered, which was the loading screens. And so I just set those on order 1,000. So I think that's actually a good question because we didn't have that problem because we don't have to add a lot of separate things to the UI.
예. 그 아까 제일 처음에 데이터가 하나씩만 있고 다 모아서 있어서 작업 시간을 단축했다 뭐 이렇게 말씀하셨는데 그러면 이제 유저들 중에 해킹 같은 거를 할 때 너무 쉬워져서 좀 그런 단점이 있는 것 같은데 그런 부분에 대해서 어떻게 좀 좋은 방법을 생각한 게 있으신지 뭐 보통 서버로 통째로 옮기거나 구조를 이제 모아져 있는 걸 막 다 쪼개놓고 뭐 그렇게 해결을 하던데 뭐 생각하시는 그 기존의 개발 방법 스타일을 유지하면서 해결하신 방법이 있는지 궁금합니다.
So we are a very simple game. We are a game that ships on console and PC. And if you're on mobile, data is a much bigger deal for you. You have to deal with things like people trying to figure out the spawn rates of a gacha box. But we don't have to worry about that. For us, if the players understand what's in the data or they change the data, that's not a problem. That's their game and that's their computer, and so if they want to make tanks do 1,000 damage, I'm okay with that. Now, we only use LiveData during development. The shipped version of the game never contacts the servers. And so no one actually knows outside of the office where that server is. We never ship that URL in the game's binary, but what we do ship is the packed flat buffer. And that packed flat buffer does have error correction on it. And we will not load it if the error correction returns that it's failed. Which means that you could hack things by changing values in the game, damage values or units, but you could not send that to anyone else without just having them also copy and paste the file. So we don't have hacking concerns because our situation is much simpler. If you're working on mobile, your situation is probably a lot harder. I'm sorry, I actually don't have any help for you. Please, I love questions. More questions, please. All right, well, thank you everyone for listening. And if you have any questions, please talk to me afterwards.